Hello everyone, we're moving on to part 4 of chapter 2, which is about the second half of section 2.2 in your textbook. We have two objectives for this video. First, we're going to be exploring the terms acid and base and the pH scale, and then we're going to be talking about some different ways that we can talk about the concentration of a solution. So the formal definitions of acids and bases are listed here. Acids are things that release hydrogen ions into water or the solvent, and bases are things that accept hydrogen ions. We can also think of bases as things that release OH negative or hydroxide ions. So I'm guessing you guys have seen the pH scale at some point in the past. We know that pH of 7 is considered neutral. If the pH is less than 7, somewhere between 1 and 6.9, then we're looking at an acidic solution. And if the pH is greater than 7 but less than 14, which is the maximum of the scale, then we have a basic solution. What we know in these is when the pH is 7, when the pH is neutral, that the amount of hydrogen ions balance out the number of hydroxide ions. When the hydrogen ions are greater in concentration than the hydroxide ions, then we have an acidic solution. And then the reverse is true for a basic solution. When the hydroxide ions are a greater concentration than the hydrogen ions, then we have something basic. It's important to remember that pH is a log scale, and what that means is between any two adjacent numbers on the pH scale, we actually have a 10 times difference in concentration. So let's look at what that means. If we were to consider a solution with a pH of 6 as compared with the solution of pH 7, we would interpret that to mean we have a 10 times increase in the number of hydrogen ions. Also, between pH 7, right here, my pointer comes back, pH 7 and pH 8, we have a 10 times difference in hydrogen ions there. Between pH 8 and pH 9, between any 2 points on the pH scale that are whole numbers, we have a 10 times difference in hydrogen ions and also hydroxide ions. Okay. Between pH 6 and pH 8, if we have a 10 times difference between this interval and also a 10 times difference between this interval, 10 times 10 is 100. So we would have a 100 times difference between pH 6 and pH 8. We can go further and look at between pH 6 and pH 9, and we see 1,000 times difference there. So if you see a question about this on an exam, for instance, what is the difference in concentration of hydroxide ions between pH 8 and pH 11? I recommend you draw a real quick sketch of a scale and write in 10, 100, 1,000, whatever it is that gets you from the interval between the first two units to the interval that you're concerned about, and just draw it out. That's the simplest way. You don't have to memorize anything if you just draw a quick sketch. Oh, before we move on, buffers are chemical solutions that resist a change in pH. So they are able to absorb and release hydrogen ions and hydroxide ions to maintain a fairly steady pH level. And our blood in particular has buffers in it that keep it at a very constant pH. I will tell you, one of my pet peeves, I can't stand it, is when people talk about the alkaline diet or the alkalizing water. It's nonsense. If the pH of your blood actually changed, that's deadly. You don't want the pH of your blood to change. So if you ever see any diet that is telling you to eat different things to change the pH of your blood, or somebody is trying to sell you supplements in some MLM scheme to change the pH of your blood, please call them out and tell them they're being ignorant. You do not want the pH of your blood to change. It will make you dead. So this is a nice depiction of what we have at various points on the pH scale. So we know that water is right in the middle, okay? It's slightly acidic. We have milk, black coffee. Maybe you guys know someone who coffee gives them an upset stomach, and so they have to avoid it. It's because it's acidic. We've got bananas and tomatoes. Some other fruits and vegetables will fall into this range. And then wine and vinegar. Everybody knows lemon juice is pretty acidic. Orange juice is also right here in this range. Your stomach acid is way down here. Very, very acidic. So again, if you eat something with the intent to alkalize your blood, the acid of your stomach is strong enough that it's just not going to change the pH of your blood. And then hydrochloric acid is just hydrogen and chloride ions together. That's one of the strongest acids, pH of 0. Going the other direction, we have egg whites as slightly basic. So if anyone has ever egged your car and you didn't clean it off quickly and the egg damaged the paint on your car, it's because it's slightly basic. Pretty standard, bleach and ammonia. We generally associate those things with bases. Oven cleaner is a very, very strong base, can damage your skin, can damage your eyes, just like a strong acid can. And then sodium hydroxide, NaOH, is one of the strongest bases. Okay, and moving on to some ways that we can measure concentration. Okay, so the first one that's important for us is weight per volume. So it's really simple. What's the weight or mass of some solid, and what is the volume that we're dumping it into? So you might see something like milligrams per deciliter. That's, for instance, the way we would report somebody's cholesterol. So very simply, the weight dumped into the volume. Percentage is similar. If we're looking for a 5% dextrose solution, we're going to use 5 grams in 100, or it could be 50 grams in 1,000, any units that give us that 5% ratio. We use 70% ethanol in my lab all the time to clean things. So that's going to be, if I'm making 100 milliliters of solution, it's going to be 70 milliliters of ethanol, and then the remainder 30 milliliters made up of distilled water. When we talk about electrolytes, we use a very specific unit. It's called equivalence. Okay, so an equivalent is the amount of an electrolyte that will neutralize 1 mole of hydrogen ions or hydroxide ions. And we can also use the 1,000th of this and talk about milli-equivalents if we're talking about low concentrations of ions like we would see in a biological system. So we could say that if we are using sodium ions, 1 millimole is equal to 1 milliequivalent per liter.